AI workloads make Kubernetes more powerful and more exposed. Models, GPUs, pipelines, and data services all become part of the attack surface. In this topic, we'll secure that foundation with isolation, policy, visibility, and trusted deployments. You've already built the broader security foundation: identity, applications, APIs, data, and cloud controls. Now we bring those controls into Kubernetes, where many enterprise AI workloads actually run, and where misconfiguration can scale quickly. Think of Kubernetes as the operating system for AI workloads. Inference services, training jobs, RAG pipelines, and data processing depend on it to place pods, reach services, scale capacity, and access secrets, GPUs, models, and data. That power is exactly why Kubernetes security matters. A weak policy, exposed service, overprivileged pod, or untrusted image can lead to model theft, data exposure, compute abuse, or lateral movement. Protection has to span build, deploy, runtime, and network. Container hardening means giving each workload just enough power to run, and no more. For AI jobs, needing GPUs, fast storage, or special libraries does not justify root access or privileged mode. Start with non-root users, read-only file systems, dropped capabilities, and privilege escalation disabled. Be especially cautious with host networking, host namespaces, and host path mounts. Kubernetes pod security standards help make these expectations consistent. Namespaces are a useful first layer for separating AI workloads, but they are not a security boundary by themselves. Treat development, training, RAG, inference, and production as separate trust zones. Then add guardrails. Resource quotas and limit ranges control CPU, memory, and scarce GPUs, reducing noisy neighbor risk. For identity, do not rely on the default service account. Use dedicated service accounts, least privilege RBAC, and workload identity mapping so each workload reaches only the cloud resources it truly needs. Network policies turn the Kubernetes network into a least privilege environment. For sensitive AI namespaces, begin by denying ingress and egress by default. Then allow only the flows the workload actually needs. Inference to the model server, RAG to the vector database, pipelines to the model store, and approved outbound calls. Labels matter here because selectors define what is protected. A mislabeled pod can accidentally bypass controls or break critical communication. When a pod needs cloud resources, it should not carry a password or access key. Instead, it runs as a Kubernetes service account that Cloud IAM trusts. The cloud exchanges that workload identity for a short-lived token scoped to one role. That role allows only the required buckets, keys, databases, logs, or model artifacts. Kubernetes RBAC controls in-cluster actions, while Cloud IAM controls external access. Runtime security starts with a realistic assumption. Prevention will not catch everything. A vulnerable library, malicious image, or stolen token can turn a normal container into an active threat. Behavioral monitoring looks for what changes after deployment. Unexpected shells, new processes, crypto mining, sensitive file access, strange outbound connections, or attempts to touch host namespaces and file systems. Tools using syscall data and eBPF can capture these signals and enrich alerts with pod, namespace, service account, image, and node context. Runtime detection becomes valuable when alerts lead to action. If a container shows known malicious behavior, enforce policy by blocking the action or terminating the workload. Then contain the blast radius with restrictive network rules around the pod or namespace. At the same time, preserve evidence. Image details, commands, logs, and events. For AI systems, prioritize model weights, datasets, vector credentials, GPU usage, and inference logs, then route findings into SEM, SOAR, and incident workflows. Every AI container is an artifact that should prove where it came from and whether it changed. During the build, capture source, dependencies, SBOMs, and vulnerability scan results. Then sign the image and store it only in trusted registries. At deployment time, Kubernetes admission controls verify the signature and provenance before allowing the workload to run. This turns supply chain security into an enforceable gate, not a manual checklist. Model-serving containers deserve extra scrutiny because they touch prompts, embeddings, outputs, and model artifacts. Start with approved base images for your serving stack, then pin exact digests instead of mutable tags like latest. Deploy only images built by trusted pipelines and pulled from approved registries. Finally, rebuild, scan, sign, and patch regularly so framework, driver, and package vulnerabilities do not become inference layer entry points. Admission controllers are the checkpoint between a deployment request and a running workload. They evaluate the resource before Kubernetes persists it, then allow or reject it based on policy. That means privileged pods, host namespaces, dangerous capabilities, untrusted images, missing labels, or absent resource limits can be stopped early. Tools like OPA Gatekeeper, Caverno, and native cloud controls turn security requirements into automated deployment time decisions, reducing what can reach runtime. For AI workloads, admission policy makes those decisions concrete. It can reject unsigned or public images before they run, keep GPU jobs inside approved namespaces with quotas, and stop pods from using host mounts or privileged mode. It can also require resource limits, network labels, and trusted service accounts. The result is simple. Security standards become automatic deployment checks. Inside Kubernetes, a service mesh makes every internal call identity aware. MTLS encrypts traffic and proves which workload is speaking, so an API cannot impersonate an embedding service or model server. Authorization uses workload identity, namespace, service account, and route to allow only expected paths, such as a RAG API reaching the vector database. The mesh also shapes behavior with retries, timeouts, rate limits, and circuit breakers, while producing metrics, traces, and logs for investigation. Kubernetes becomes safe for AI when security is layered. Hardened pods, least privilege identities, segmented networks, trusted images, admission controls, runtime detection, and service mesh protections. Together, these controls make the platform governed, auditable, and resilient. Next, we apply this thinking to GPUs, model registries, vector databases, and training pipelines.